Hello, welcome to FlexGuard tutorial. Today we'll be doing our second example on beams, shear force and bending moment. Considering concentrated load, this is the example 2 for concentrated loads. You can check our other tutorial to get the introduction to know the types of load, types of supports before proceeding to this tutorial to understand much better of what we mean by concentrated load. So the question says a beam 10 meter long is simply supported at its end and carries concentrated loads of 30 kN and 50 kN at a distance of 3 meters from each end. Draw the shear force and bending moment diagram. So before we proceed to drawing of the shearing force and bending moment diagrams, the first thing we have to do is to interpret the question. And for we to interpret the question, we have to draw a sketch of what the question is talking about. So from the question, a beam 10 meter long is simply supported. So that means we have a beam. So simply supported, that means we are going to have at its ends. So we are going to have this, and the length is 10 meter. So from here we can draw 10 meter. So we are through with the first part. So the second part, they say it carries a concentrated loads of 30 kN and 50 kN at distance of 3 meters from each end. This is the first end, this is the second end. So in this case, the first end is 30 kN. So we can have this, our load from this point, load of 30. So here will be our 3 meter. Then from the other end, we have the load of 50 kN. So we can have our 50 here. So the same distance here is what? 3 meters. So 3 plus 3 will give us 6. So definitely here will be 4 meters, which is the total span of the beam, which is 3 plus 4, that is 7 plus 3, which will give us 10. So we are through with the interpretation of the question. The next thing we have to do now is to calculate our reactions. So for we to calculate our reactions, we have to get some points. In this case, we'll be assuming that our upward forces will be assumed as positive, while our downward forces will be assumed as negative. And if we are going in a clockwise direction, we'll assume it as positive, and if we are going in an anti-clockwise direction, we'll take everything as negative. So for we to proceed to calculate our reactions, let's draw a mini equation for this beam. So let's call this point our point A, and let's call this point our point B. So definitely the reaction at point A plus reaction at point B is equal to the sum of the total forces on the beam, and we have two forces on the beam, or two load on the beam, which is what? Our 30 kN plus our 50 kN, which is equal to 80. So we can tag this as our equation 1. So from here, summation of horizontal forces in this case is equal to 0. Summation of f of x is equal to 0. So likewise, we don't need to calculate for the horizontal forces in this case. So let's proceed to our moment. So summation of forces along the z-axis at point A is equal to 0. This implies that I'm going to take my moment from point A, so everything will be moving towards the direction of point A. So from our assumption earlier, I will say we are going in a clockwise direction. We'll be having we'll consider it as positive. Going in an anti-clockwise direction, we'll consider it as negative. So if I'm taking moment from B, this is point B, you can see the mass at point B, and I'm moving to point A. I'm going in an anti-clockwise direction. So I'm going to have, it's going, so your reactions is moving from point B to A in an anti-clockwise direction. So we're going to have minus 10 of RB. That the 10 is the total span, plus 50 is moving in a clockwise direction to point A, and the total span from 50, this point of 50 to A is what? 4 plus 3, which is 7. So we're going to have 50 times 7. Then likewise, the other force, which is 30, from 30 to point A is 3 meters. So we are going to have 30 times 3, all is equal to 0 from here, because everything is equal to 0. So from here you can see and observe that 50 times 7 will give us 350, 30 times 3 will give us 90. So 350 plus 90 will give us 440. So we can proceed and have minus 10 of reaction at B plus 440 all is equal to 0. So from basic elementary mathematics, you can make arbitrary the formula by dividing both sides by minus 10 after collecting like terms. So we move our 440 to the other side. We'll have RB is equal to minus 440 divided by minus 10, which will give us 44. Don't forget all forces, all loads are in kilonewton regarding the forces also. So from here, to make it easy, there's no need of you taking moment from point B again to do all these long calculations. All you have to do is proceed to this equation we generated earlier, which is our equation 1, which we have reaction at A plus reaction at B is equal to 80. So at this point, we have gotten reaction at B. So just substitute the value of reaction at B into the equation. We now have this. We now have our RB, which is equal to 44 kilonewton. We'll substitute into the equation. We now have RA is equal to 80 minus 44, which is equal to 36 kilonewton. So after calculation of the reactions at the necessary ends and the supports, we'll now go to the main part of the question, which says we should draw the shear force and bending moment diagram. So let's reproduce our beam again. So create a sketch of this nature. So we have already gotten a reaction. We have gotten the reaction at point A and at point B. So the next thing is to calculate your shear force using a simple formula. So we assume that the shear force will target as F. So let's calculate the shear force at F1, that is at this point. Observe where the pen is at this point. For we to get the shear force at this point is equivalent to the reaction we got at this point. And the reaction we got at this point is what? 36. And at this point is 44. So we'll have the first point at this point as our 36. So we have gotten the shear force at the first point. So for the first point, we say it's equal to F1, which is equal to 36. So let's now move to the second part, F2, which will now say what is now the F1. Now earlier I told you that we assume that all downward forces are negative forces. So at this point 30 kilonewton is acting downward, so it's a negative force. So I'm going to have 36 F1 minus 30, which will give us 6 kilonewton. So the force is going to move. The first reaction will move for a distance of 3 meters, then act downward to a point of 6. So we'll call here our point 6, that's 6 kilonewton. So we'll now move to the third part, which will now be what? The reaction at F1 minus the downward load at the first 3 meters minus. So we are going to move for a distance of 4 meters to this point, where we'll have our 50 kilonewton, which is acting downward. So definitely it will be minus 50 since the force is acting downward, which will now give us 6 minus 50 will give us minus 44. So this force will move, this 50 load at the point of this beam will act on this load and bring it to this point. Let's call this the minus 44 point. So this will move for another 3 meters to this point. And if you observe, we have a reaction at this point, which is 44. So the final force, which is our F4, will now be equal to what? F1 minus 30 minus 50 minus the second F2. That is reaction at point B, which will be equal to, that is F2 is minus 44, and we have 36 minus 30 minus 50, which will give us minus 44. And we said our upward forces is considered positive, so our F2 is coming with a positive sign. So minus 44 plus 44 will be equal to 0. So we'll now return this back to this point called 0. So we are through with the shear force diagram. The next thing is to proceed to the bending moment diagram, and in this case we'll be considering a very simple method which is very fast. You don't need to create an equation for your bending moment. All you have to do is to consider the areas of these various shapes with their length, and we'll get the required bending moment. So we are back. All we have to do now is to get the bending moments diagram, and for it to do that we'll use a simple method, so which is our area method. As you can see, this particular shape is rectangular in nature. Same thing applicable to here, same thing applicable to here. But in some cases you might observe you have things like triangle, trapezium. If you have trapezium, you can divide into many sections. In our next example we'll touch something like that so that you can understand how this works. You can have a parabola and how to use other methods to solve them. So let's consider the bending moment for the first part. Let's reproduce the rectangle. You can see a rectangle of this nature which have a breadth of 36, a length of 3 meters. And the formula for area of a triangle, area of a rectangle is what? Length times breadth. So our length is 3 meters and the breadth is 36. So I'm going to have 3 times 36, which is equal to 108 kilonewton meter. You all know that moment is defined as force times perpendicular distance. So that is why you are seeing the unit in this form. So I'll move to this point and draw. Since it's a point load to the rectangle, it will be in form of triangular shape. It's slanting upward. So I'll write my 108 at this point. So we move to the second point, which is at this point. So we'll also reproduce the rectangle. We'll have something like this. The length is 4 meters and the height or the breadth is 6. So same thing, length times breadth. So in this case I'm going to have 4 times 6, which is equal to 24. But using this method, you will not just go and write for 24 at this point straight. All you have to do, since here is positive, we'll add the sum of these two moments together. So we have 108 plus 24, which will give us 132 kilonewton meter. So we'll move to the last part, which will also have a rectangular nature. Also we have minus 44 as our breadth and 3 meters as our length. So in this case we'll have our length times breadth. Our length is 3 meters, so we have 3 times the load, 3 times minus 44, which is equal to minus 132. So as I said earlier, these forces were positive but added. In this case here is positive, so I have 132 plus what do I have here? It's negative, so minus 132. From basic mass you can see that 132 we have plus and minus. Plus times minus will give us minus, so definitely I'm going to have 0 kilonewton at this point. So here we have 132. So drawing your diagram, here will move upward. So at this point here will be our 132, and finally it's returning back to 0. So we are through with the bending moment diagram. All you have to do is just to create some hashing in the beam. So here is negative, here is positive, here is positive. So that is all. Please endeavor to click the subscribe button as we await for our next tutorial on other types of beams, like a beam carrying varying distributed load, uniformly distributed load, a cantilever with a UDL on it, a cantilever with VDL, and all other type of tutorial regarding strength of